All righty, welcome to the 42nd Slither. I am just thrilled that I got the number 42. Has a lot of deep meaning to me on lots of different levels. But we're not here to talk about Hitchhiker's Guide to the Universe or Galaxy Universe, one of those. Yeah, good grief. Wow, it's Tuesday and late in the semester. Or baseball. We're here to talk about inorganic labs. So that's just a great thing for us to be chatting about, and we're going to just kind of share some of our favorite labs that we've taught, what we like about them, maybe what we don't like about them. We won't go too deep into the weeds of, what's our least favorite part of lab. We all know it's grading lab reports, but maybe we can offer some insights. We have a special guest who's got a seminar to run to here quick, so I'm going to turn it over to Shirley here right away, and then we'll just kind of take turns and riff and share and see where we go from here. So go ahead, Shirley, lead us off.
Thanks, Chip. It's great to see everybody. So nice to be able to just hop on and talk to our community. So I'm sorry to be missing some of your discussions. I'll be pretty quick with mine. I just want to point out that I was recently a co-author on a publication in JChemEd, and I'm putting the link into the chat now. And I think, Chip, you'll probably add those to the notes in YouTube if you're interested. So if you want to click on that, it is part of a special issue on new visions for teaching chemistry laboratory. And this is an exercise that Melanie Teicher and I developed when we were doing general chemistry in fall 2021. And the idea was to take a traditional cookbook style lab and to put in some guided inquiry parts to it. And what was kind of near and dear to our hearts was that this particular experiment had to do with something that we teach, especially to our midshipmen at the Naval Academy, which has to do with Navy boiler water. And part of that process is that on ships with boilers, they do actually titrate the boiler water to make sure that it is at the proper pH and it has the right ratio of phosphate and hydrogen phosphate for it to function optimally. And for years and years, we've taught this as a traditional experiment where students don't understand which volume of nitric acid titrant should be used to figure out the total phosphate concentration. And our goal in the redesign was to actually help them design their own experiment so that it would be more clear to them which volume of titrant was necessary and why. And this involved taking a one-day lab where we shoved in, 4 different titrations and spreading it all out into 3 weeks, including a day, part of a day of lab. Our labs are 2 hours long, where the students got in small groups and made their experimental designs together after having done a potentiometric titration so that they could better understand what was happening at each point along the titration curve. So those are some of the things. I'm happy to share more details or answer any questions people have, or I could share my screen so you could see some of the figures. Anything that you're interested in would be great.
So there's actually a reason for government delays in keeping things from 1 week to 3 week. There's good sound pedagogical evidence for doing that.
That's a good question, Chip. As much pedagogical evidence as we have for anything else that we do. How about that?
Good enough. How many times have you run that?
Last fall was the first time, and then I was fortunate enough to teach the course again this fall with a different instructor as my partner, another Ionic Viper member, Matt Buck. So he and I are doing the course this semester, and we were able to refine a little bit what we did and see some see some different improvements. One of the issues is when you add indicators, we wanted them to decide, because you do need 2 different indicators to see the different equivalence points that are happening during the titration. So it was really nice that in a previous lab that led up to this one, we incorporated a demo where we showed them what happens when you add 2 indicators to 1 test tube of the same pH. And we chose examples where it really didn't come out well, right? Things look kind of muddy, brown, red, and here we got to talk about why it's okay to add 2 indicators and at what points we would do so. So that was really, really nice. And Matt had never, run this lab before because he wasn't in the course last fall, in fall 2021. And he actually said it was one of the most rewarding sort of teaching experiences that he'd had, which is just high praise, right? Like when you put the time into coming up with new lab experiences, you hope that it's positive for the students and for the instructors.
Are you getting samples from different ships and different boilers, or?
This is terrible. It's not real boiler water. The lab staff mixes it up so that it's free of some of the other components that we don't need and might interfere with, some of the work. But it's nice because we do titrate for chloride, we titrate for oxygen, and we also do conductivity in addition to the hydrogen phosphate titration.
Cool. Well, I didn't mean to monopolize that. Any other questions for Shirley?
What's the next lab that you want to put guided inquiry into?
Hi, Jacob. Yeah, that's a great question. So we actually redesigned the whole semester of lab so that it's centered around this theme of observation and measurement. And instead of having a lab that goes with each chapter, roughly of the book that we're doing, we just sort of said the lab doesn't follow the lecture portions at all, even though they're one combined course and they're taught by the same instructor for the students. We just said we're doing our own thing in lab, and so we organized the lab. The first half of the semester is based on titration. The second half is based on UV Vis. So we incorporated some guided inquiry components to UV Vis as well, including an experience where they got to come up with a procedure to build their own calibration curve to analyze the amount of food dye in a sample.
Okay, thank you.
So I've got a question. So I've kind of been toying around with doing more, we'll say student designed experiments in our integrated lab, but it's kind of like if I'm going from something that's 1 week to something that's 3 or 4 weeks, kind of what's the trade-off? What do you've got to get rid of 3 other experiments in order to do that one experiment.
Absolutely. These are the hard decisions, right? Like, as a consequence, we didn't do really an equilibrium related lab, even though we could have done one that was UV Vis related. Like, that's something that we could kind of go back and do. Yeah, there are trade-offs, and the goal was to see if we can engage the students more. A lot of the students who are taking the accelerated Gen Chem semester have had college chemistry experiences before. So what we're trying to do is give them value added by giving them the naval applications and also this more unique lab experience. So it's always a hard call. And I know that it's a bigger conversation. For instance, I'm not sure I would recommend that we take that approach for our big Gen Chem course that has, the 1,000 students versus the 70 students. So with 1,000 students, I think that it would be much harder for everyone to be engaged in the design process. Here we were able to really, really focus the students' efforts through this, building up all these different titration and other experiences to get to that capstone experience for this half of the semester. So it is definitely full, as you said, full of trade-offs. But it sounds like in an integrated lab situation like you have, Kate, that there could be really cool things you could do to pull in different parts of your curriculum into one culminating experience, and be cool to hear about that.
It's on my list of things in the future.
All right. Thanks, Shirley. Kate, we'll put you on the spot and turn to you and see what you want to share with us.
Okay, let me see. Oops. Can I share my screen?
I can probably give you that power in just a second. All right, you should have the power.
All right. There we go. So I guess, disclaimer, I don't teach in inorganic lab. I teach a dynamics lab. But we make quantum dots because they're fun and they're colorful and they're inorganic. And they also fill that requirement of, macromolecules and et ceteras. And I kind of took the synthesis from these two published papers. So it's one that's you don't need an Earth atmosphere, and they're really fast. So it's easy to do them in our basically no equipment lab. And so basically you heat up to 225. So we use a sand bath so no oil catches on fire. Kind of helps to get them preheated because sometimes they take a long time. Add selenium. The reaction's done in 2 or 3 minutes. So we only have enough hood space to have 1 or 2 groups of students to run the reaction at the same time. But because it's over in 2 or 3 minutes, it doesn't matter that they take turns to do the experiment, and we still have way more than enough time for everyone to kind of run through the experiment. And so you just sort of take with a pipette, just kind of take out samples, and then the reaction stops when they cool off. So you kind of go from, a yellow color to way here in the back, kind of a reddish color just as the dots get bigger. So they can kind of see, see the change by eye. If you've got, a black light, you can, see the fluorescence of them. And then actual real student data. So what we do is we take absorption spectra and emission spectra. And so you can see, the band gap transition, in the absorption and the emission. This one, they didn't quite have enough solution in the cuvette. So you're kind of sampling the edge of the solution. And we did have to use, so the plastic cuvettes are fine. The oleic acid and octadecene don't dissolve anything, but you have to use the small volume ones. Otherwise you don't have enough solution. And then from there, there's like an empirical formula you can use to calculate diameter from your absorption or from your emission. If you were doing a more PChem class, you can, make them use particle in a sphere and calculate it that way. I was not that mean. And this part is, no one quite got the point of this part, but I wanted them to see that the growth is not really linear. So they all put linear fits on their data and said, yes, it's linear. Okay, so we may need to work on that part of the experiments. And then if you had, we don't have the ability, but if you had like, dynamic light scattering or, TEM or something like that, you could then compare actual size to size that you're getting from spectroscopy. But, it's a nice, fun, colorful, pretty colors. Everyone likes it. It doesn't, no one's staying late on this day. Yes, Shirley.
Oh, I will lower my hand. So I don't know very much about quantum dot syntheses. A couple of questions. So you get a distribution of sizes, is that correct?
So when you're taking out, as far as, if we're talking like research grade quantum dots, yeah, I'm sure there's a pretty broad distribution of sizes, but, our spectra are relatively narrow, and that, if you're taking out the samples pretty quickly, you get a not so broad, at least spectrum. I'm sure, again, if we measured, looked at dynamic light scattering or looked at like, TEM of the particles, they wouldn't look perfect. And sometimes you see in the emission spectra, especially, depending on the student, sometimes you see a lot of emission from trap states. So they're not, the world's most perfect and beautiful particles, but it's a nice fast synthesis that gets the job done.
And my second question was, is there a way to do this with microwave heating? I think I've read that there are some methods out there, but I
I'm
don't.
pretty sure there are, like, I think, for, again, doing, like, we'll say research grade particles, I think you can. I've never tried because we don't have one, but I'm pretty sure I've seen that you can. I suppose in that case, you would just do a separate, I'm gonna, stick this one in the reactor for a minute, this one for 5 minutes, this one for, however long. Because I mean, with I guess with it just being an open flask, it's pretty easy to just take the samples out as far as instead of doing multiple reactions. But I'm sure there's a way you could do it with the microwave as well. See, if we give me a minute, I can find the links to those papers. They're both JChem Ed papers.
Yeah, that would be great. I'll try and keep a running tally of different links, so when I make the official Viper LO of this, that we get them all linked. I think I can pull that off. All right. Other questions for Kate? Do you get the traditional selenium smells too bad, or
Not too. I mean, so we're dealing with small volumes and keep everything in the hood. And actually the selenium takes a while to dissolve. I think there's probably redox chemistry happening as well. So I usually have the TA make that the day before, and then the students are just adding the solution into their cadmium.
all right. Dean, I don't know if you had one you wanted to share with us, or just
Sure.
or two. We got time.
I was like, which one? So, I mean, so I don't know whether I should go ahead and share a screen. It might be easier to talk about.
I can certainly give you that power also eventually. All right, you should be set.
Let me try that. Let's do that. Yeah, let's just do this. And so this is a lab I've done a couple times. This is adapted from a, everybody see that?
Yep.
Let me scroll back up to the top here. Here we go. So this is adapted from a Viper synthesis and characterization of cobalt spinels that was posted a while back. I've done it a couple times. What I like about it is I do another lab using the solid state model kits. So that's something that we can connect to that. I also have, I don't have them use it, but I have the polyhedral model kit as well, so that I can at least show them those types of models as well. But what I like about it is it lets everybody, or actually, no, I guess everybody, yeah, I'm trying to think when I did this last time, everybody gets a different composition to synthesize. So there's a whole family of spinels. They all have the same overall structure, but a different collection of cations. And so everybody's has to calculate their own stoichiometry to begin with, and then grind it up, and then we put them all in the oven. But then you get out in the end, I don't know whether am I showing up enough for you to see the vial here? Where is it? So some of them are a nice sort of aqua color. There's some very deep blues. There's some that are sort of boring grays, but anyways, so they get a lot of different colors, which is always good. And then they so that's the synthesis part, and then we do powder X-ray diffraction and indexing. So they don't, these students actually, it's interesting, the last times I've taught this. I also teach a crystallography course. So the course is actually, there's usually 3 or 4 students in both courses. So I don't know whether I'll try and coordinate that. I haven't quite thought that through yet. But they get in this class, at least they get a little bit, and talk about indexing. There's an Excel, I have an Excel spreadsheet, which makes it relatively easy. You know, they put in all your peak positions, and then hopefully with a little bit of manipulation, they can figure out, okay, yeah, there's a pattern here that I can see. So that's what this goes through. There's actually a couple, I don't think I have them in here, but there's a couple good YouTube videos online about, just the basics of indexing powder patterns. So that's always good. And then let me see, I was going to pull up, I think I have, yeah, so this is, zoom out a little bit. So these are just, so different people had different compositions. So you can see one group, I don't know, they had some impurity. That first one, I'm not sure what was going on. But you can see that, they can see their data, they can see the other groups, they can see that there's sort of similarity in the overall pattern, but there's you can also see the shift relative to each other. That is real. That's not just a sample preparation issue. And they also can, after they collect their data, they can search a basic search function that they can use. And it usually comes up, if not with the exact match, with a closely related compound. So that's sort of most of it. So I haven't decided if I usually try and add something or tweak something every year. I haven't looked over to see whether I'll do anything more with this lab this year or not.
Shirley snuck in a question before she had to run.
Oh, okay,
yeah. Basically, how important is the X-ray? And I'm gathering from this last slide, it's kind of important.
Yeah, I think I mean, the reality is, I like to talk about the single crystal stuff, but the reality, it's more likely that our students are going to see powder. If they're going to see X-ray, more likely that they'll see powder in some way or another. So I think it's important that they are at least, maybe exposed isn't the right word. At least they've seen it in some form or another.
Oh, we like exposing our students to X-rays. That's always good, for sure.
Yeah.
Cool. Thank you.
Yeah.
Well, I'll take a little different approach here for a minute or 3, and then come back and see if Kate and Dean have anything else they want to share. Jacob is kind of here getting ready to run his first inorganic lab, so he's looking to glean some knowledge. Hopefully we'll provide some. So my perspective, rather than a favorite lab, is kind of so what labs do you think about choosing? My lab course is tied to a sophomore level course, and I kind of start with some baby quantum, kind of the bridge between Gen Chem quantum and P-Chem quantum, which doesn't necessarily line up great with labs, especially the first week. So some labs work in really well with what we're covering in class. Some labs don't work so well, but they're just fun to do. So I think we kind of touched on this one. You got to have something that gives lots of fun colors, because it's an inorganic lab. That's what it's all about. Kate had a great one. I've traditionally done the jobs method lab, which is on Viper. You can look at the students just love the colors in that lab. It's very very colorful. They're very surprised to see the blues and the purples and that sort of thing. So that's a fun one. I think Dean mentioned, doing a lab kind of with the crystal kits, and I do that too. If you're teaching solid state structure, I think that's a great time for them to really sit down and look at things and get an appreciation for holes and occupancy and all that kind of stuff. Not being a solid state chemist, I took the zinc oxide nanoparticle off of Viper, which I think is a good one. Although I like Kate's more because it's got colors. The zinc oxide is, as you can imagine, not super colorful, but I really liked it because we have a powder diffractometer on campus, but it's in geology. So I'd always get the students excited to say we were going on a field trip for lab that week. It's 2 buildings over. So they were a little grumpy about me setting them up for going somewhere besides the geology building, although most of them hadn't been in that. I agree with Dean. I think it's important that they see that, and the powder aspect I think is really cool. We usually have good lab battles of who gets the nicest sample of zinc oxide and gets the best match from fitting the library. And every once in a while, a student does something unexpected and their pattern, I think they scraped the glassware too hard, because it wasn't zinc oxide that was coming up at all, which was fun and exciting. We did recently get a single crystal instrument. So one that I've added because we got that is the resolution of the trisethylene diamine cobalt isomers. And I ran it for the first time last year, and it was really, really cool. Basically, you get to the point of the crystallization, leave them there a week, come back, humongous crystals. We took them over and it was like, bam, structures in seconds, pretty much. So I thought that was good. But really, to kind of throw in one that I really think is good and important is just doing some computational stuff throughout the lab. I do one with molecular orbitals that I think really gives students a much better appreciation for what we calculate quick and dirty with group theory. We'll often tie in kind of the IR aspects, and they'll look at the stretches and I go, look at those funny little symbols on the sides, like these A1s and B primes and that kind of stuff. In my senior level course, we'll talk about what those means and where they come from. So that's always a fun kind of tie-in. But I do think it helps them visualize something that's kind of abstract, especially when, in lecture, as I'm doing it via group theory. And, I can say the molecular orbital is spread over the entire molecule, but, I know my artistic skills might not necessarily do that, but for them to get it and see it and be able to manipulate it in 3 dimensions, I think it's a great added benefit to them. So a bunch in quick hit, but those are some of the ones that I like to think about. Anyone else have any ones they want to add or talk about a little bit more?
So
Say my favorite.
Nope.
Go ahead, Dean.
Sorry. So what kind of molecules do you, in your computational lab, do you start small and work up, or?
Yeah, we do. When they're really looking at the MOs in it, it's small. It's 7 atoms or less generally. When I do a lab with a Lewis acid base adduct, where we go into the IR, and we will do the MO calculations. Of course, those take longer, so generally I have the files saved for them ahead of time, but they can still look at and manipulate them. I don't want them to get too lost and look at MOs in those kind of molecules, but we do look at the IR, the vibrationals, frequencies, the different types of motions. They always love to see their molecules wiggling and dancing around on the screen, for sure.
Definitely. Yeah.
Go ahead, Kate.
I was gonna say one of my favorite, I guess, day one, week one experiments. I've either done make a bunch of different inorganic pigments. Again, they're all colorful, and it basically, here's how we accurately measure and calculate percent yield, because somehow that's fallen out of their head since Gen Chem. And then you can turn them into paints, and we can paint pictures with them. Last time I taught the class, we kind of added in cyanotyping, so you can make Prussian blue, or you can photochemically make it. You can do cyanotypes. Works better when our lab is in the fall, because it's nice and warm and sunny out at the beginning of the semester. When we're out there in January, hoping that there's enough sun to develop our cyanotype, it's a little.
Yeah, we have somebody who teaches a chemistry and art, and so that if it's in the winter, they'll just like be lined up in the hallway on the sunny side of the building because it's too cold outside. Yeah,
nice.
Yeah, so as a backup plan, I have a little full spectrum light for the plant in my office, because I have no window. So I'm like, I can always bring that down, and we can just take turns shining it under the light bulbs.
One other lab that I've done a couple different versions of is a MOF synthesis. That's usually pretty good early on, because it's in terms of technique, they're all pretty straightforward. Usually, solvothermal, where you just put things in an oven at 90 degrees or something like that. So some of them make really nice. I think there's a JChem Ed that you just throw it in and you get really nice crystals that you can actually throw on a diffractometer pretty easily. So, yeah.
Yeah, my first lab of the semester is a little bit weird. The long-standing tradition is class is Monday, Wednesday, Friday, lab is Tuesday morning. So my first lab we've had one lecture. I generally have just barely kind of started talking about isotopes and how mass spec is a way to look at different isotopes. So our first lab is usually just very simple. We run a GC mass spec of a mixture of something. My favorite mixture, possibly slightly biased in this, is a mixture of ferrocene, ruthenacine, and osmocene. They separate it out really nicely on the column, and then basically they're sitting there trying to figure out. I give them some hints as to what roughly the formula is, and it's between like 8 and 12 carbons and 8 and 12 hydrogens and some transition metal, and the transition metals in the same group, so they do a little bit of plug chug, figure out roughly what works to get the molecular ion peak they see. And then I have them go and like, okay, now find the metal and see if you can identify the different isotopes that are present and calculate the atomic mass of the metal from the different isotopes and their relative mass ratios. It never comes out super good. We don't exactly have the best GC mass in the world, so I'm not terribly surprised by that, but it's a good exercise for them to think about. And I kind of like getting that first one tied right into class, because then I can sell them on stuff that doesn't tie in too well later.
No,
Getting invaded by a student. We're doing demos for middle school kids here in a little bit, so we're making some liquid nitrogen ice cream. Always good stuff. Never underestimate the power of a donut when you're doing an 8 a.m. computational lab either. Good bribe. They always seem to appreciate that. So what are you thinking of teaching in your senior level course, Jacob? Just got it outlined here at this point, or?
Well, I've got a couple ideas. I do like the CAD solenoid quantum dots, because I do have, between myself and some of my colleagues, a lot of us are interested in luminescence. So we do have above average luminescence toys for a PUI. I got my hands on a near IR detector, so we can look at the really big quantum dots if we want to. So that's definitely interesting. A MOF synthesis using solvothermal, that could work. But I'm a little curious about the single crystal aspect. So I do have, from my career, I have a couple of crystal structures that I think would be good for students to just try and refine. And Chip and Dean, how do you get around the problem of students having Macs to get them refining structures?
In what sense?
Because I remember from grad school, the professor that taught our physical inorganic class wanted us to do our own crystal structure refinements. So he would give us data and we go through. And if you have Windows, it was no problem. If you had a Mac, ShellX tends to not play as nice.
I've never had any issues. Do you use a Mac?
I do not use a Mac. I haven't had them refined because I'm dealing with sophomores, and I think it's a little more than I'd want them to try and do. But to my knowledge, OLX2 will run on a Mac.
Yeah,
Oh, yeah, OLX will work. Okay, yeah,
Yeah.
that's a good way to do it.
And worst case, OLX has built-in refinement,
Yeah,
which is slower but reasonable. The solution built into OLX is fine, but it's a little spotty.
it's not ShellX.
It's not. Yeah, ShellX.
Yes.
I literally had to change my crystallography, my example problems because ShellX got too good. It used to be.
Yeah,
Yeah.
If you do intrinsic phasing with
once ShellXT came out.
Yeah.
With the
That's it. Yeah,
intrinsic
XT.
phasing, yeah. It would just got it right every time, and it's like, oh, okay, I need harder examples.
Yeah. But I've got a couple examples of like I have a wonder how easily I could find it. But there's one of my lab mates gave me a compound that was a rather large organic molecule, not super big. So it's not something that's typically that difficult to solve and refine, but it had an interesting case of disorder where there was a 5-membered ring that had a sulfur. And in one compound, the way that the crystal packed, the sulfur was locked in one position.
Right.
But in another compound, that sulfur has disorder where it can be in one of two directions.
Right.
So getting them to be able to spot that, I think, would make for an interesting kind of lab exercise from a dry lab perspective.
Yeah.
Is at least on that new GUI that came out for ShellX TL. I think it's called ShellX or Shell.
ShellX LE.
Yeah, LE. Yeah.
Yeah.
That you can see right away where the negative electron density is.
Yeah, that does a good job with the residual.
Yeah.
Yeah, and if you ever want, I think there's several people within the Viper community that have single crystal instruments.
I have an arrangement with Matt Zeller.
Nice.
Right. Or yeah, if you know Matt.
Yeah. He's like 3 hours away from me. Yeah.
Where are you?
I'm in southern Indiana.
Okay, yeah.
So if you think of
Matt
Indiana
used
as a
to be-
sock, I'm in the toe.
Right. Matt used to be much closer when he was in Youngstown.
Yeah, that's when I first started working with him when I was an undergrad. My advisor, well, he went to Youngstown at some point, or he grew up near Youngstown, so somehow he knew Matt and got me introduced to him, and it's been I'm glad I know him.
Mm-hmm. No,
he's definitely taught me a lot over the years. Yeah.
Yeah.
Another thing that I thought I might turn into a lab, and again, I wonder if I can find the paper really quick. Hang on. But I had these 2 tetra iron compounds where I had 2 different halides. And again, the crystal packing is different between the 2 halides. To the point where you can actually see a significantly different melting point. So having them go through, make the things, and then they can refine the data, see the crystal structure from data that I give them, and then go through and do the physical properties and see how that relates to the actual solid state structure. I think that could be interesting too. Yeah, it's something I published in Acticryst not too long ago.
Throw that into my list. Well, if I
So
had to go with
at some point, that might be a Viper LO if it works out.
there you go. That sounds good. I'll see if my colleagues will agree with me on this or not, but I would say, going into it the first time, trying one new thing sounds reasonable. Don't go crazy and try all new things.
Exactly. Yeah. These are ideas that I'm going to pick from.
Yes, good. Yeah, and then find, my plan is always, okay, which one did I hate the most this year? That's the one that's going to get replaced, and that's the way the class keeps evolving. I feel bad not having mentioned there's a phosphine chalcogenide lab on Viper also that I like, just because I like them to see phosphorus NMR and slopping around and not using deuterated solvents and getting spectra and being able to talk about, hey, look, we had one peak to begin with and now it's at a different place. We know a reaction happened. They come out of organic looking for so much, and yet there's some really simple beauty in NMR that I think they kind of lose appreciation for, looking for all these couplings and all these different patterns. So I think that's a good thing to include somewhere.
And at some point, I need to go through my predecessor's notes and try and find his labs. That has proven to be quite a challenge in itself.
Sounds like the best way is go through the old lab and like, why the heck do we have this? Oh,
there is a lot of a cobalt compound that I've found that are just in random places, all in vials. So I assume this is a lab he's been doing for 20 some years and just been storing the student samples.
Probably
it's
the cobalt isomer lab.
probably.
Exactly. Yeah, I think that's what it is, because it's a cobalt chloride with some other ancillary ligand to fill out the tetrahedron.
Well, put a note with him, save him for 100 years, and then he can get a publication like Werner did. All right. Well, I hope we gave you some thoughts and ideas and some insight. Certainly, I would encourage you and anyone out there, hop onto our Discord channel. If you have questions as you're setting up lab, want ideas. If you're running a lab and getting weird things, there's probably someone out there that's run it before. Or if you're developing a new one and want some people to test it out, I'm betting you can find some people in the community that will help you out with that also. Just a reminder to you though, Jacob, if you are developing something, we do have an agreement with JCE that it can go on Viper and still wind up in JCE later. So keep that in mind.
Okay, so I don't have to do JCE first if that does work out.
Nope, we're a great place to do some community testing first and give more data that they like to see in JCE. So certainly would encourage you to do that. Well, this was a little off the cuff kind of SLITHER. Didn't know what we'd get, but I think we had some great conversation. So thank you all for participating. Anyone have any final thoughts as we get ready to wrap it up?
Thank you for organizing it.
All right. Well, thank you all. I'll shut her down, and happy almost end of the semester to all.